Hey guys, we're going to pick up with convex mirrors today. Should be on page 12 of your packet. We did concave earlier this week, and convex are a little bit easier. And then we're also going to do the mirror equation down here, and that's what's going to be on your quiz that I'm posting today. I realized that your packet does not have lenses in it, and I thought I had put that in there when I printed it forever ago, so it might, but pretty sure it doesn't. So if you look in Google Classroom, down here I posted the workbook, okay, Unit 8 workbook. Click on that, and I said we were on page 12 today, but towards the very end we have lenses. If my computer would be faster. Okay, so this is where we are now. Concave mirrors, convex today. Okay, and then the mirror equation, and then this is a new section that I don't think you guys have printed, but it is on here digitally. So if you have a printer, awesome, you could try to print those out and then do them along with me when I post them. Probably next week, and if you don't, then still follow along and just take notes the good old-fashioned way on a piece of paper, okay? So alrighty, back to convex mirrors. So convex mirrors, they are the ones that kind of point out towards you. So if this is our object here, the reflective surface is coming out at you versus what we were doing earlier with a concave mirror where it caves in, okay? That's concave. We are now on convex. Convex. Reflective surface where the edges face away, the middle points towards you. These are easier because you're always going to get a virtual image that's smaller and upright. And so these are examples of convex mirrors. We're all familiar with them. They are located on the outside of your car. The side view mirrors, they are used for security purposes and places. I think this is an example of someone having one in a classroom so that the teacher can look up and kind of see what's going on behind her maybe, or behind him. You might see them in a hospital, like where, people are rushing around a corner with a gurney, and there would be a mirror up in the corner so that they can see if someone's coming the other way so you don't crash. Sometimes you have them when you're driving around and, to see around a curve in a car, okay? So they help you see more of what's going on around you than a plane or a concave mirror would show you. So drawing the ray diagrams, it's just like with the concave mirrors. So, I'd suggest you use two colors until you're more familiar and you with these, and you aren't making any mistakes. And your first color will be the line that will go from the top of the object to through straight to the mirror, and then through F, focal point. So if we go back here, this would be this pink line right here, okay? Difference here too is your focal point is now behind the mirror. So instead of our concave mirror where your focal point was on the same side as the object, convex, it's going to be on the other side. So everything that comes in, it focuses it on the other side, all right? Okay, so we're going to use both of our colors, blue first, to do this example. And I'm going to try to do it on here. All right, so our first line is going to go straight from the top of the object to the mirror, and then straight through F. And might be a good idea if you use a straight edge so you don't have crazy lines like I do. All right, now we're going to switch colors to red, top of the object, straight through C. That was pretty good. And our new image forms here. Okay, that's our image. Do you remember SALT? S is for size, A is for attitude, let me use L is for location and T is for type. So S, A, L, T, S to describe our image. The size, it is smaller. A, attitude, it's still upright. L, location, it is behind the mirror in front of F. And T, type, it is virtual. Virtual. Concave mirrors are easy because they will always create virtual. This is the type of image it will always create. It will always create a smaller, upright, behind the mirror virtual image. Okay, smaller, upright, behind the mirror, and virtual. Yay! All right, try another one. And, okay, this one's slightly closer to the mirror than our last one, and it's a little smaller. Go straight to the mirror and then through F. Switch colors to red. This is working much better than my last video. Straight from the top through C. And you see, even though I did a terrible job at that, we're still going to get a smaller object where they both intersect, which they kind of intersect right there. Where your red and blue lines intersect, this is your object. It's still smaller, upright, virtual, behind the mirror. There we go, smaller, upright, virtual, behind the mirror. Okay, mirror equations. So, this is the equation that we're going to use to, if I were to actually give you a distance of an object in front of a certain type of mirror, and if I were to tell you how big the radius of the mirror was or the focal point, you are able to tell me where the image is. All right? So it's 1 over F is equal to 1 over DO plus 1 over DI. F is the focus, or the focal length. I should change that, focal length. It won't let me. DO is the distance of the object. DO, distance of object. DI is distance of the image from the mirror. DI is distance of image. Distance of object, distance of image. Most of the time, I'm going to tell you where the object is and what the focal length of the mirror is, and you'll have to tell me where the image pops up. Okay? And also, don't forget that your focal point is half of the radius. So, looking here, focal point is half of the radius. So, if our radius from the mirror to C is 10 centimeters, oh gosh, erase that, need to get better at this, is 10 centimeters, then your focal length would be what? It would be 5 centimeters, okay? All right, so now focal length. For a concave mirror, the focal length is in front of the mirror, and for convex, it's behind. And for our purposes, anything that is on this side of the mirror to the right or on the same side as the observer, think of like your eyeball is here, okay? On the side of the observer, this is positive. Versus anything that is on the other side of the mirror from the observer. So observer, eyeball, okay, other side of the mirror is going to be negative. So for a concave mirror, it's on the same side as the observer, so it's positive. For a convex mirror, it's on the opposite side, so it's a negative focal length. And that matters because when we start plugging them into the equation, if you put in a positive focal length for a convex mirror, you're going to get the wrong answer. All right. Same with image, and object is always going to be on the positive side, so you don't have to worry about that. But the distance of the image, so this is DI. So if DI is negative, then that tells you it is on the opposite side of the mirror, and that would be a virtual image. Okay? If the image is a positive, if you end up with a positive DI, then it is on the same side as the observer, and it is on the same side as the object, so it will be real. Okay, so positive DI means real, negative DI means virtual. Again, for concave mirrors, that's what matters, because concave mirrors are the ones that can create real and virtual images. They can do it all. Remember, that's the makeup mirror. If you're a certain distance away from it, it will flip your image upside down and will actually create a real image. If you're closer to it and in front of it, like right here in front of F, then it will create a virtual image behind the mirror. Convex mirror will always, always, always create a negative DI. A negative DI that is in, behind the mirror, smaller upright. Okay. All right, so we have an object that is 30 centimeters in front of a concave mirror with 6 centimeter focal length. Object is 30 centimeters, that's your DI. Concave mirror with 6 centimeter focal length, so that's our F. So let's draw a ray diagram of what's going on. Concave, make sure I have my mirror right, which I do. Then next you want to draw the focal length and the radius, which is C, which is what we've been saying is C. It's the radius. And then you want to label what lengths they give you. So our focal length is 6 centimeters, and our radius is going to be, remember, radius is going to be your focal length divided, or I'm sorry, your focal length is going to be your radius divided by 2. All right, C or /R, it's the same thing. So if that's 6, then that means this is 12. And if our object is placed 30 centimeters in front of the mirror, then our object is going to be past this. Our object will be past here at 30. All right, so now let us solve this problem. Scroll down. Okay, so remember our formula is 1 over F. 1 over F is equal to 1 over DO, distance of object, plus 1 over DI, and we are solving for DI. Okay, so we are going to do 1 over our focal length, which is 6, and is that a positive or negative focal length? Let's go back up. Positive. Anything on this side, same side as the observer and the object, okay, is positive, and this would be negative. So our focal length is going to be a positive number. Is equal to 1 over 30 centimeters plus 1 over DI. And I'm sorry, we actually need to convert these centimeters to meters, so that would be 0.30 meters, and this would be 0.06 meters. All right. Let me move over here. Okay. Now let us solve for that. So 1 over 0.06, when you plug that in, should be 16.67. And that would equal 1 over 0.3, which ends up being 3 repeated, plus 1 over DI. Then you want to subtract both sides by 3.3. And then you're going to end up getting 13.37 is equal to 1 over DI. And we want DI, so what you're going to do is multiply both sides by DI, and then and then divide both sides by 13.7. 0.37. Okay, so what you should get is, let me erase some of this and then I'll write that down. So what you should have is DI is equal to 1 over 13.37. When you plug that in, you get a DI of 1 over 0.075 meters. Okay, so our distance of our image is positive, so that means our image will pop up on this side. So it will be a real image, and all real images are inverted. So that means it will be 0.075 meters, so that's technically what, 7, so it'll probably pop up about right here. 7 centimeters, so that's in between our 6 and 12. Okay? All right, now moving on to the back of page 12, so page 13, magnification. This is to find how much your mirror magnifies something, if it blows it up really big like a makeup mirror would, or if it has the ability to shrink something and make it look smaller. So this is the equation that you're going to use to find magnification of an image, the height of the image. So we have hi is height of image, and ho is height of the object. So this will tell you if your image will be bigger or smaller than the object itself, and that tells us if it magnifies it. So hi over ho is equal to negative di over do. Okay, so positive and negative height images, or hi. If you have a positive hi, then that means it will be upright. And if you have a negative hi, that means it will be inverted. It will be upside down. All right, remember when you draw your images, they are always from this principal axis, this middle line. So if you end up with a real inverted image with a concave mirror like you can have, then it will end up being a negative number. All right, so let's try this example, and we're going to draw it and solve for it as well. So we have a 4 centimeter tall light bulb that is placed at a distance of 8.3 centimeters from a concave mirror, having focal length of 15.2 centimeters. Determine the image distance and image size. Image distance and image size. So first off, let's list out everything that we know about these givens and unknowns. Let me zoom in a little bit. Okay, so 4 centimeter tall light bulb placed that distance from the object. So this, or from the mirror. So this is our object. This is how tall it is. So that's going to be, that is going to be the height of our object, HO. This is the distance away that it is. So this is our DI. Concave mirror. Remember, concave mirror has a positive focal point. So it's going to be positive. Determine the image distance, so DI, and the image size, so HI. Height of the image and distance of the image. So first off, we will need to use our mirror equation to find one of these. And then we'll use our magnification equation. Okay, so let's list out our givens and unknowns first. We have HO is equal to 4 centimeters, and we're just going to keep everything in centimeters for this one, so we don't have to do any unit conversions. Since it gave it all to us in centimeters, that's okay. Distance of object was 8.3 centimeters. And our focal length was 15.2 centimeters. And we need to find HI, and we need to find DI. So we need to figure out what this image is going to be. Okay, so let's draw this first. Let's draw this scenario first, and then I'll go to a blank slide and solve for it. So we have a concave mirror. Okay, looks like this. Draw your focal and your radius. I'll just go to R since it's what we're more used to than C. So our focal length is going to be 15.2. So that means our radius is going to be twice that. So it's going to be 30.4. Just make sure, yep, 30.4. Our object is located at 8.3. So our object is actually located, remember that they gave that to us, 8.3. They gave us 15, so everything's in reference from the mirror itself. So if the mirror is 0 and this is 15, this is 30, then our object is actually going to be in front of the mirror. Okay, based off of your knowledge on ray diagrams, you should be able to draw this this ray diagram so that you can double check and make sure that when you do the math, that the math matches what you have already drawn. This is what you'll need to do for your test. Okay, so top of object to the image, or to the mirror, and then straight through F. Let me switch colors like we're used to. Top to object, straight through R. So remember this, if they are getting farther and farther apart like this, that means they're never going to meet on this side. So that tells you need to extend your lines this way. Right, and make sure you use a ruler so that you don't end up with crazy things like this. Okay, so our object is going to be where they intersect right there. This will be, or this is my image. All right, so my image should be virtual. Virtual distance, so that means it will have a negative DI, and it should be enlarged. Okay, so my HI should be, my height of my image should be larger than my height of my object. My height of my object was 4 centimeters, and if my image is going to be enlarged and much larger than that, then it should be greater than 4. Okay. Okay, so let us actually solve for this now that we know that how to draw that ray diagram. So first we need to use our mirror formula. So first let me zoom in so I can draw this a bit better. Okay, so our mirror formula was 1 over F is equal to 1 over DO plus 1 over DI. All right, our focal length was 15.2. So we should have 1 over 15.2, and we're just going to leave everything in centimeters for right now, over our distance of our object, which was 8.3 centimeters, plus 1 over DI. Okay, plug that into your calculator. You should get 1 over 15.2 is 0.066 is equal to 1 over 8.3, which is 0.12, plus 1 over DI. Okay, so you're going to subtract both sides by 0.12, and then that should give you, I just had it, 0.066 minus 0.12. That will be negative 0.054 equal to 1 over di. All right. And then multiply both sides by di, and then divide both sides by 0.054, and basically you need to flip these two in order to solve for your di. di is going to equal 1 over 0.054, and when you plug that in, you should get a di of negative 18.5 centimeters. Okay, and this checks out with what we had said back here with our ray diagram. Remember, our object was located here, but our image popped up on the other side. Our image location we said was going to be negative because it was virtual, and that checks out. Our di, our image distance, is negative 18. That means our image will pop up negative in the virtual side. All right, so now we need to solve for hi. We have di, now we need to solve for hi, and we're going to use our magnification equation. This one, m is equal to hi over ho is equal to negative di over do. That negative is part of the equation, which is very important because you can see that our di that we have now is negative, so when we plug it into our equation, both those negatives will cancel out. Okay, so let me move to this side. Oh goodness, stay with me guys. Okay. All right, we're gonna draw. So, we're going to use magnification equation, which is hi over ho is equal to negative di over do. Our hi was, oh, that's what we're trying to find. We're trying to find hi. Our ho, though, height of the object, was 4 centimeters. Our di was negative 18.5 centimeters, so those both cancel out. Those negatives cancel out, and our do, which is what they gave us, was 8.3 centimeters. All right, all these are in centimeters, just leave them in centimeters, it's fine. Okay, so we have this. You can do some cross multiplication if you would like to, or however you would like to solve this. I think I did cross multiplication. So I did 8.3 times hi is equal to 18.5 times 4. And I ended up with an hi, a height of my image of 8.9 centimeters. 8.9. Okay. So let's double check with our ray diagram to make sure that that checks out. If we are to zoom out if I can. My goodness. Okay. Our image was supposed to be larger than our object. All right. So this was our object. We were supposed to find image size and was larger. Virtual, negative di, larger, greater than the height of our object. And that is what we got. Okay. All right. So let's do this one. Concave mirror. I'll add my face back in. Concave mirror is, there we go. Zoom is frustrating me. Okay, concave mirror. So concave, right? That is going to be that type of mirror, concave, where you have the focal point here, radius here. This time it tells us that the radius is 20 centimeters, so you need to remember that the focal point is the radius divided by 2. So if our radius is 20, then that means our focus is going to be 10, and that's a positive focal length, right? This is the positive side, this is the negative side. 2 centimeter tall object, 30 centimeters from the mirror. So two different things going on here. This is how tall the object is, 2 centimeters, so that's going to be the height of the object, HO. And 30 centimeters from the mirror, so that's the distance of the object, DO. So we want to know the image position and the image height. So again, we're going to be solving for the distance of the image and the height of the image, just like the last one. Okay, so let's, again, since we have our focal length, we already figured that out. Let's do our ray diagram first and then make sure that our numbers that we solve for make sense with the ray diagram. So if our object is 30 centimeters from the mirror, then that means our object is going to be way out here. Okay, 30 centimeters. Again, they told us the radius was 20, and if our object is located 30 centimeters from it, then that means our object is going to be past R, or past C. It's going to be right here. That's our object. Okay, so let us draw our ray diagrams. So top of the object straight to the mirror through F, change colors, top of the object straight through C, or our radius, and your new image, I'll do purple, should form right there. So we should be getting an image that is a positive DI because it is real, and all real images are upside down inverted, so we should have a negative HI for inverted. Okay, inverted. All right, so let's do the math to make sure that all of that checks out. Okay. So we had, let's do all of our givens and unknowns first. Finally getting the hang of this. So our givens, we figured out that if the focal length was 10 centimeters and that the DO was given to us was 0. Oh, I put it in meters. Let me not do that in meters. Let me keep it in centimeters. Was 30 centimeters, and we had the height of the object was 2. And so we want to find HI, height of image, and DI, distance of image. Okay, so first we need to use the mirror equation in order to find DI, and then we'll use the magnification equation to use to find HI, just like we did for the last one. So mirror equation is 1 over F, which is 10, is equal to 1 over DO plus DI. So our DO is 30 plus 1 over DI. Okay, so that should give you why did I do this in meters? So 1 over 10, 1 over 30, all right, minus both sides, so 0.0667, 1 over DI. That means your DI is going to be equal to 1 over 0.0667. So then your DI should be 15 centimeters is DI. And that's positive, so that checks out with our DI. Okay. Oops. So Now let's do our magnification equation where we're going to solve for hi. Hi over ho, which was 2, is equal to negative di over do, which was, what was our do? 0.3? No, 30. Okay, so 15 divided by 30, that's going to be 0.5 times 2. It's going to be 1, but negative 1. So our hi is going to be negative 1 centimeters. So that's inverted, and it's also smaller. So let's make sure that that checks out with our ray diagram, and it does. Our ray diagram showed that it was inverted, positive, so real, inverted, and it was going to be smaller than our actual object. It's actually half the size. So our actual object was 2 centimeters, and we got that this was 1. Okay, I'm gonna let you guys do this one. I'll post I'll write the pictures, or I'm sorry, I'll write the answers on here. So for this example, this is example 3, you should get, no, this is example 4. You should get a di of negative 0.091 meters, or 9.1 centimeters if you don't want to convert. And you should get an hi of 0.01 meters, or 1 centimeter. Okay, your practice is to do the rest of those practice problems, and on your, really is to finish this packet, except for you might have a lab in the very back. Obviously we can't do that, but you are going to finish this page that had all the ray diagrams on it. Okay, I'll post the solutions because we have convex that are on the back of this too. And more importantly, on the next page you have 1 through 9 problems, and I want you to do all of those. Okay,